In last class, we had seen concepts of remote sensing. We had seen the elements of remote sensing. We had seen the transmission of an EMR, electromagnetic radiation. We had seen reflection of the wave, and we had seen the refraction of the wave. So next topic is about scattering. Scattering occurs. Scattering occurs when particles or large gas molecules present in the atmosphere interact with the electromagnetic radiation, and it redirects from its original path. So that leads to scattering. The scattering depends upon several factors like wavelength of radiation, more abundance of particles or gases present in the atmosphere, the distance that the radiation travels through the atmosphere. You can see in the diagram that we have the earth which is present. So above the earth we have the atmosphere. So whatever falls on this atmosphere, due to the presence of particles or large gaseous molecules, they tend to interact with them and they move away, so which can be given in three forms. One is Rayleigh scattering as such, Rayleigh scattering. Second one, Mie scattering. Third one, Mie scattering due to larger particles. And whatever the deflection that occurs due to this are being classified into Rayleigh scatterings. And other than the Rayleigh scattering and Mie scattering, if there is any other scattering, that comes under non-selective scattering. Okay, types of scatterings. So what is a Rayleigh scattering is? Scattering consisting of the wavelength, which is 1 by lambda power 4. If that condition is satisfied, then that particular electromagnetic wave is having Rayleigh scattering. Or you can say that this obeys Rayleigh's scattering law, the electromagnetic wave radiation that is being propagating in space. This is due to the scattering from atmospheric molecules, where the dominant are at elevations of 9 to 10 km from above the surface, which I had shown in the last class diagram. That follows a wavelength dependency of the frequency. This Rayleigh scattering causes the blue color of the sky and the red color at sunset. During sunrise, it will be red color or orangish color. During sunset, it will be reddish color, and during daytime, it will be blue color. So that is due to the Rayleigh scattering. So the intensity of Rayleigh scattering varies with 1 by lambda power 4. So you can see that wavelength is being put up in x-axis, right from 0.4 to 0.7, where the visible light spectrum is taken blue, green, yellow, orange, and red. Is the variation right from 0.48 micrometer to 0.67 micrometer wavelength. So the intensity of scattered light will be higher near 0.4 micrometers where the energy in electron volts is measured at this. So how much energy is measured is that it is above 3, near 0.4. It is 2.5 electron volts is variation occurs at zero point 0.5 micrometer wavelength, and at red or 0.67 micrometer, the energy in electron volt is only 2 electron volts. So this is your Rayleigh scattering intensity variation. You can see the Rayleigh scattering are due to the presence of particles, where the diameter of the particles is very much less than the wavelength of the electromagnetic wave radiation. So like small pecks of dust or nitrogen or oxygen, when they are present, they create Rayleigh scattering. You can see that in the diagram below. You can see that we have a sun, which is your radiating electromagnetic wave region. So it focuses on the earth surface. So during sun time, sunrise, during sunset, you can see how it is present, and during noon time how it is present. Okay. So what happens? I'll show you that in the diagram. So Rayleigh scattering causes shorter wavelengths of energy to be scattered much more than the longer wavelengths. This scattering causes shorter wavelengths of energy to be scattered much compared to longer wavelengths. So whereas Rayleigh scattering is the dominant scattering mechanism in the upper atmosphere, the fact that the sky appears blue during the day is because of this phenomena. So you can see that phenomena. The blue light is being falling, then the angle theta 1 is present. When the red light is falling, there is an angle of only theta 2. This shows that the blue during daytime is being absorbed more. Okay, due to more scattering of blue light. You can see that. A clear blue sky. So blue radiation is around 0.46. Red radiation is around 0.66. In daytime, your sky will look like this because blue is scattered 4 times greater than red radiation. So clear blue sky. You can see this. Why the sky is blue during daytime? So when the electromagnetic wave radiation that falls from the sun towards the earth, when it reaches the earth's surface, the spherical behavior of the Vibgya spectrum is that blue scatters more, blue color scatters more. Okay, this is why only the other colors falls on the earth, and only the blue will scatter around the atmosphere. So this will make the sky to be look like blue during daytime. So scattering of electromagnetic waves. So you get the reason behind why the sky is looking blue. The atmosphere scatters blue light more effectively than the red light. Hence, blue light reaches your eye when you look at the sky. You can see there. The earth is there. On the earth, a person is present. When he looks the sky during daytime, you can see red to be falling directly, whereas blue scatters more. So this is why it looks bluish at daytime. During evening or morning, how it looks, we'll see. So at sunset or sunrise, solar radiation will be traveling a longer path through the atmosphere. Viewing a setting sun, the energy reaches the observer is largely depleted of blue radiation, leaving mostly red wavelengths. So the dust, smoke, additional scat adds additional scattering with a wavelength dependence that increases the red sky effect, which we call as MIE effect, M-I-E. Okay, during sunrise or sunset, you can see orangish or reddish, which is that the energy that reaches the observer would always deplete the blue radiation. So wherever we see, we get only red. Or red wavelengths will be scattering more during that period. So it appears red. You can see how it works. The atmosphere scatters light blue more effectively than the red light, so which is known to us. So hence mostly red light reaches your eye when you look through a thick slice of atmosphere at the setting sun. You can see how the sun is set. Sun is getting set. Okay. So only the red will reach to the observer. You can see this also. Why the sun looks red. After the Rayleigh scattering and the condition for bluish sky structure and reddish sky structure we have seen, we are moving on to the Mie scattering. So the Rayleigh scattering are due to the gaseous molecules, as already stated, oxygen or nitrogen would give more scattering, which is present in the atmosphere, right from 2 to 10 kilometers altitude. So here the Mie scattering occurs due to the smoke or dust being present, where the particles diameter are approximately equal to the wavelength d is equal to 1. The major sources of causing the Mie scattering are the water vapor and the dust contents in the atmosphere, where the Mie scattering tends to influence longer wavelengths, which is a common in lower atmosphere. This Mie scattering is common in lower atmosphere where large particles are mostly present and dominates over overcast conditions. So you can see C, you can see A as your gas molecules in Rayleigh scattering, B as your smoke and dust. Depending upon the diameter, D is equal to 1. Depending upon that, Mie scattering will occur. And the third one, C, is your non-selective scattering due to water vapor. We'll see the Mie scattering first. Diameter of particles would be equal to the wavelength of the electromagnetic wave radiation due to dust, smoke, and water vapors. So these dust, smoke, water vapors are the common cause of Mie scattering, which tends to often affect the longer wavelengths than those affected by the Rayleigh scattering. So the Mie scattering occurs mostly in lower portions of the atmosphere. The specifications of the Mie scattering. The particles will have a mean diameter ranging from 0.1 to 10 times the incident wavelength. Examples are given. Scattering intensity is proportional to 1 by lambda power 4 to 1 by lambda power naught, which is 1, depending upon the particle diameter. So a clear atmosphere would have both Rayleigh scattering and Mie scattering, MIE scattering, which combined together is giving an influence of about lambda power minus 0.7 to lambda power minus 2. So these are the two scattering. Apart from these two scattering, we have another scattering called non-selective scattering. The particles that are much larger than the wavelengths, having diameter greater than 1, where the droplets, water vapor droplets in the atmosphere ranges between 5 to 100 micrometers with large dust particles. Always this non-selective scattering is independent of wavelength, where all the wavelengths are scattered equally. So a cloud appearing as white would be a non-selective scattering that scatters all visible and near to mid infrared wavelengths. So this is an example. We have the Earth at the bottom. Earth. A cloud is present between the sensor which is being deployed in a satellite in space. And other clouds are being present that are being interrupted. So when the sun radiance falls us, this cloud will appear as an obstacle. So where the electromagnetic wave radiation will reflect, reflect or diverge or absorb even. The clouds can absorb. So the diameter of the particles would be very much larger than the wavelength of electromagnetic wave radiation. Other droplets, large dust particles, and so. So this occurs when the particles are much larger than the wavelength of the radiation. Hence, the water droplets and the large dust particles can cause this type of scattering. So the non-selective scattering gets its name from the fact that all wavelengths are scattered equally, equal scattering in all directions and in equal amplitudes. This is an example of the non-selective scattering. This always independent of wavelength lambda power naught. The aerosol particles greater than the wavelength, for example, 10 times. Aerosol particles, aerosol particles much larger than the wavelength, greater than 10, is a best example of a non-selective scattering. Examples are water droplets, ice crystals, volcanic ash, smog, which are present in space. You can see a port is there, and you can see the sky, which is clear in nature, and in some part it is going to heavily rain, where water droplets may occur with the larger sizes. In some places, ice crystals. So these are the best examples of a non-selective scattering. You can see the characteristics also. So if you have any doubts, you can put in chat box. Then I'll proceed further with the graph. Okay, thank you, Sai Ganesh. I'll proceed further. So this graph is an relation between the wavelength of different regions, ultraviolet, VGR, and infrared. That with the scattering, how much amount of scattering can be done, or how much of scattering is being done depending upon the particles, ranging from lambda power naught to lambda power minus 4 or 1 by lambda power 4. You can see at ultraviolet region, you can see there is a higher scattering, relative scattering, you can see that. Whereas when you see at the blue region, you can see that there is more scattering, Rayleigh scattering is found at lambda 1 by lambda power 4, because this follows Rayleigh scattering law. Okay, so that is being kept as separate. So the region between lambda power minus 2 to lambda power minus 0.1, okay, is your clear real atmosphere, the region. So we can see that this band from approximately 0.56 or 57 micrometer to around 0.92 micrometer of wavelength gives you a clear atmosphere, in the sense we get good amount of non-scattering. Clear real atmosphere in the sense scattering is very much lesser. So this region can be used for better utilization or acquisition of your data. So this is the meaning. So if you see that it comes under your greenish reddish green region to photographic or infrared region or the thermal infrared region. So from this you can able to understand which type of system can be used for capturing your image or acquiring your information or acquisition of data for remote sensing. So depending upon the application you need to choose. Why? Because from this region, right from here, you can see that 0.5 to 0.98 or 97, till there you have a clear real atmosphere where even though the real scattering is very much lower and there is an relative scattering is very much lesser. So this region can be utilized. This is what the illustration is. So you can see what happens in the atmospheric scattering when a gaseous molecule is present. You can see the wavelength. The wavelength will be like this, it will go like this. So when a smoke or dust is there, the wave will go like this. You can see. When an water vapor non-selective is there, depending upon the wavelength, it will go like this. Okay. So the types of scattering encountered in atmospheric is the wavelength of the incident radiant energy, that depends upon the size of the gas molecule, dust particle or water vapor that comes in between it. So that decides what type of scattering it is. But our system should adapt or find what scattering is there and what frequency range that we need to use depending upon the wavelength. Okay. So what happens if scattering is present? Let our electromagnetic wave radiation move. Let it fall it on the sun. Let it fall it on the object. Let it fall on the processing unit or the hardware. What does it mean to a remote sensing person, or what does it mean to the engineer or the scientist who wants to get this data? What happens is that if scattering is present, that will cause results in remote sensed images. Remotely sensed images that we acquire, it will be showing an inappropriate values. There will be a decrease in the spatial detail, the exact detail of that location or that particular place that we are remote sensing. That image will have lower resolution. There would be an improvement in the contrast of the images. So that I'll show you also in an application of remote sensing how this spatial resolution is being used and what region if you see how it looks. Okay, don't do not worry about this contrast. So after the scattering, let us see about the absorption. Absorption is the process of absorbing or is the process where the radiant energy is absorbed and converted into other forms of energy as I had shown in the diagram in yesterday's class. The atmosphere prevents or strongly attenuates the transmission of radiation through the atmosphere. The atmosphere will prevent or attenuate or will refract through the atmosphere. So an absorption band is a range of wavelengths or frequencies in the electromagnetic spectrum within which the radiant energy is absorbed by substances, water molecules, carbon dioxide, oxides, nitrous oxides, oxygen, and so, and it goes on. So these all will absorb the electromagnetic wave energy that is being propagated through them. So what does this H2O, what is this oxide, what is this carbon dioxide absorb? Or where there can be observed is that O3 will absorb ultraviolet radiation in high atmospheres, oxides. As I shown in the diagram, a graph in the stress gas, oxides, carbon dioxide, and water droplets, how they are being present in atmosphere, a graph. So that expansion is that oxides are nearly present at ultraviolet radiation region, whereas carbon dioxide are or carbon dioxide can be measured at mid and far infrared region, which is 13 to 17.5 micrometer in the lower atmosphere, whereas water droplets H2O are observed at mid-infrared region from 5.5 to 7 micrometers and then greater than 27 micrometers in lower atmosphere, depending upon the size or the diameter of the water droplet. You can see absorption for an H2O. Okay. The vibration process, a small displacements of the atoms from their equilibrium position will occur at wavelength 3.106. You can see everything will be in H2O. Everything will be in stable, intact condition. So whereas when it goes in wavelength of 2.903, you can see that O2 molecule will move towards H molecule. You can see from the diagram. Whereas if you go towards another wavelength 6.08 micrometer, you can see that everything is in opposite. You can see the difference. This direction is the flow of your attraction. Okay, you can see that. So this creates a vibrational process. From this we can identify the presence of water molecules. Absorption is this. Absorption is the main mechanism where electromagnetic wave radiation interacts with the atmosphere. In contrast to the scattering, this phenomenon causes molecules in the atmosphere to absorb energy at different wavelengths There are three major absorbents: oxides, carbon dioxide, and your H2O. The oxides are the ozone layer, which absorbs the harmful radiation, especially the ultraviolet radiation from the sun. The ozone layer does that. The carbon dioxide absorbs radiation strongly in the infrared region that are associated with the thermal heating that serves to trap this heat inside the atmosphere. The water droplets or the water vapor in the atmosphere absorbs much of the incoming longer infrared and shorter microwave radiation that are harmful to human life. So these are the functions of each and every ions being present in Earth, present on the surface of the Earth. Absorption, part of the electromagnetic spectrum heavily affected by the scattering and absorption that has become useful for the remote sensing. You can see wavelength. Wavelength versus the solar radiation. The solar radiation at the top of the atmosphere is around 0.4 micrometer, and solar radiation at sea level is at zero point 0.5 micrometer, having solar radiation of about 1500 Weber per meter square per micrometer. You can see this graph. Ozone layer or the oxides, H2O, water content, oxygen content, the absorption bands. In the previous class, I had shown you in black and white, the same in color, differentiated. Ozone, oxygen separately, nitrous oxide separately, water molecule, water droplet separately, atmosphere separately. Absorption bands by different gases in different layers of atmosphere. We're going to have a view on this. Kindly go through, then I'll proceed. Any queries you can type in chat box. Thank you, Kitana. Okay, thank you, Kitana. So since no courage, I proceed further. The same transmission, reflection, scattering we are seeing. I'm adding absorption in this. Okay. Transmission, when an electromagnetic wave travels from one medium to another medium at an angle theta, or the critical angle if it is present, then transmission will occur with an angle. Okay. And if everything is reflected back, theta 1 is equal to theta 2, you will get a reflection. Reflecting angle will become, so theta 1 is equal to theta 2. Scattering is that diffuse scattering due to rough surface and smooth surface scattering. And we have seen the different types of scattering mechanisms also. Rayleigh scattering, Mie scattering, and non-selective scattering. Then absorption is your this diagram. Emission as well as refraction. And metals will absorb something. Water molecules, ozons, and your nitrous, carbon dioxide will all absorb electromagnetic wave radiations. Okay. So how do we calculate this transmission? So atmospheric transmission and in terms of percentage can be calculated by transmitted energy divided by input energy. The remaining amount of energy after being absorbed and scattered by the atmosphere is transmitted. So you can see for different wavelengths what is being absorbed more. From 0 to 22 micrometer wavelength, the transmittance taken from 0 to 100 will be like this. Okay. At 3 micrometer, water and carbon dioxide. At 5, carbon dioxide. At 7 micrometer, water. At 10 micrometer, ozone. At 15 micrometer, carbon dioxide. At 21 micrometer, everything is wavelength measurements, water. So depending upon the requirement, you can choose which wavelength to opt for its application. So atmospheric windows, the transmission band. Since atmospheric transmittance, the same in color. That's all. How it acts in ultraviolet region, how it is in visible, how it is in infrared region, till the microwave radar. Everything is measured in wavelengths. So the atmospheric windows refers to the relativity transparent wavelength regions of the atmosphere. So the wavelengths at which the electromagnetic wave radiation are partially or wholly transmitted through the atmosphere are called as atmospheric windows. In some rare cases only we get 100% of transmission. Most of the cases we get only a partial transmission of electromagnetic wave. So that wavelength we call it as atmospheric windows wavelength. Atmospheric windows for upper ultraviolet region and the photographic infrared region till that wavelength of 0.3 micrometer to 1 micrometer approximately can be utilized. The reflected infrared region are we used for reflection are 1.3 micrometer, 1.6 micrometer, 2.2 micrometer. At 3 to 5 micrometers and 8 to 14 micrometers, the thermal infrared region is present. And above 500 micrometers, sorry, 5000 micrometers, microwave region is utilized. So depending upon the need and object that we want to remotely sense, we need to use these regions. You can see this diagram will give you an exact representation of where the electromagnetic spectrum is present, what are the different bands, L band, S band, C band, X band, what are the typical satellites being deployed, for example at C band, RadarSat 1, ERS, Sat 1 in X band aircraft typically are being utilized. This is your atmospheric window. You can see a home or a house which is present in the Earth surface. On the Earth surface, you can see that all the sun's radiations that never falls on the Earth surface. Why? Because gamma rays, X rays will be filtered out by this layers. UV rays, ozone layer will filter it out. It reflect it back. Only the visible light, infrared region, and the radio waves will be propagating onto the Earth surface. Okay, you can see the window. For radio waves, no blocking. It will free flowly. It will transmit. Infrared region only a partial, not all. Visible light, everything will pass onto the Earth's surface from the sun. UV region, not all, only one or two regions, blue. Okay, that one. X-rays completely eliminated. Gamma rays completely eliminated. This is a small illustrative diagram of atmospheric window. Next is the water vaporization. So how water vaporization starts? Water vapor absorption. The water molecule will have three classical frequencies, which is V1, V2, and V3, that corresponds to three different wavelengths. As I had seen, as I had shown you, symmetric word stretch at 3.106 micrometer. It's not mm, it should be micrometer. And lambda 2 wavelength is 6.08 HH bending, and at wavelength 2.903 micrometer asymmetric word stretch. So these three classical frequencies we get during water vapor absorption. So when electromagnetic radiation falls on the water vapor in space, so at these wavelengths, these three occur. So totally can have a wavelength of around 1.87 micrometer. As an example is taken. You can see that in the diagram. You can see the Earth, the gamma rays, X-rays, ultraviolet rays are blocked by the upper atmosphere, whereas visible light, observable observable from Earth with some atmospheric distortion can be done. Most of the infrared spectrum are absorbed by the atmospheric gases. Radio waves can be observable from Earth. Long wavelength radio waves are being blocked. The brown color represents your brownish yellow or yellowish brown represents your Earth surface. Blue is your sky, and the satellites are being deployed above the space. So for best viewing of information of that can be taken only from the satellites in space. And above you have the different wavelengths at which all these works is being given. Gamma rays, X rays, UV rays are around 1.1 nanometer to 10 nanometer. Visible spectra around 1 micrometer. Infrared spectrum around 50 micrometer to 1 millimeter. Radio waves that are observable from Earth is around 5 centimeter to 10 meters, and the long wavelength radio waves are always blocked. Okay. This is the same diagram that we had seen. So what do we get from this atmospheric windows is that the atmosphere will strongly absorb from this. What we can understand is that the X-rays, gamma rays, and the ultraviolet rays are very strongly absorbed in the atmosphere itself. It never reaches the Earth's surface. Whereas gamma rays and infrared rays are somewhat lessly absorbed, or you can say that they are not strongly absorbed in atmosphere. Whereas the atmosphere, the informations about the ultraviolet and the visible spectrum, near infrared regions, the mid infrared region, far infrared region, microwave region, having this specifications in micrometers. Everything is in micrometer. This is a typological error. I'll change it. Everything is in micrometers. Are very much importantly considered by designing a remote sensing sensor. So depending upon the wavelength, depending upon the application, the frequency is to be decided. Depending upon the frequency, the sensor is to be used. So with this, the electromagnetic wave radiation with the atmosphere, which you have seen, electromagnetic wave radiation interaction with atmosphere. This topic is over. Electromagnetic radiation interaction with atmosphere. So any queries, type in chat box.